So we'll do a little bit of counting. We now ask, we were saying Gell-Mann had to find 8 matrices, traceless Hermitian matrices for SU3. But we could easily now jump to SUN and ask how many n by n Hermitian traceless matrices. How many? Okay, so this is easy. So first there are the diagonal elements, and there are n minus 1 independent objects we can write down, right? The minus 1 is because it has to be traceless, so that subtracts 1 from n. And the other thing is how many elements are here in the off diagonal, n times n minus 1 over 2, because these guys are related to that guy by Hermitian conjugation, right? It's Hermitian conjugate. But we must remember this, we have to multiply by 2 because these entries are complex numbers, and each complex number is 2 real degrees of freedom. So this is n squared minus n. And so altogether, this and this, you add these two and you find that they're n squared minus 1 such matrices. Okay, so now we can write down, we can make a little table. So how many such matrices there are. So for SUN, and here I write n equal to 2, 3, 4, 5, 6, and so on. And so this is 3 and 8, 15, 24, and 35, and so on. So, for example, this 3 is Mr. Pauli, and these 8 are Mr. Gell-Mann. And then afterwards, physicists stop naming them after people. And so these numbers play very important role. For example, if you believe in SU5 grand unified theory, there are 24 gauge bosons. And that's where the number comes from. And if you believe in Cron SU3, which is QCD, there are 8 gluons. Okay. So the 3 we already know are these Pauli matrices. But now we can have it's instructive to compare with SON. So SON, I remind you, is n by n is generated by n by n matrices that are antisymmetric, real and antisymmetric. So the number of such matrices is n times n minus 1 over 2. Okay, so for n equal to 2, which is the trivial case, SO2, of course there's only one such matrix, that's rotation around the fixed axis, and 3, 4, 5, and 6. So this is 3, 6, 10, 15, and so on. Okay, so if you look at this table, you can see there's a famous, these 3 others are equal. And so this is the famous and mysterious local isomorphism between SU2 and SO3. Okay, so this is how SU2 and Pauli matrices have to do with rotations in quantum mechanics. And when I say local isomorphism, this means that the algebra is the same, but not at the level of the group. It's at the level of the algebra, not at group, not the level of the group. And so this we'll certainly discuss more, that's very important in physics, more soon. Okay. So the proof of this, you can just give a very quick heuristic proof if you're just hand-waving proof, is that these are two Lie algebras, and both Lie algebras have street generators. And so there are only so many Lie algebras with simple Lie algebras. So they must be isomorphic. That's of course not a rigorous proof, and not even rigorous enough for physicists. So, but yes? More soon, I'm going to discuss more about this point soon. Yeah. Yeah, that's exactly the next thing I was going to come to. Okay, so but now you notice another remarkable coincidence. In general, these numbers, as you can see, these numbers are not the same. But then you see this, as the student pointed out, this 15 appears. So the question is whether SU4 is isomorphic, locally isomorphic to SO6. So locally, we use this symbol for locally isomorphic. So now, if you believe heuristic arguments, now the heuristic arguments is maybe not so strong, since these have 15 generators and may have complicated structure. So it's an exercise again for the students. This is probably the most difficult exercise today, which is to prove or disprove. So you could either try to prove this local isomorphism or disprove it. They have the same number of generators. Are they the same algebra? Okay. So now I'm going to do the more soon. I'm now going to show the isomorphism between SU2 and SO3. And this is a very famous construction, one of the most beautiful constructions in physics and in mathematics to show that these two algebras are isomorphic. Okay, so consider a matrix X, which is a linear combination of the three Pauli matrices. So X, Y, Z are three real numbers. Now, if sigma 1, sigma 2, and sigma 3, the three Pauli matrices, are traceless Hermitian, this implies that X is also traceless Hermitian. So let U belongs to the group SU2, and here I'm talking about group. Okay, the group SU2. So U is an element, a unitary matrix, okay, with determinant equal to 1. Then we consider X prime equal to U dagger XU. So that's the definition of X prime. Now we claim that X prime is also traceless Hermitian. Now traceless is easy to find, so just check. Easy to prove, sorry. Trace X prime is trace of u dagger x u. And now you use this important property of the trace, which is that the trace is cyclic. You can move the matrices together. And this is u dagger x. And then you use the property that u is unitary. And so this is equal to trace x. And since x is traceless, x prime is also traceless. Okay? So now the determinant is also equal to, I'm sorry, so it's Hermitian, and its Hermitian is, to show that it's Hermitian is obvious because x prime dagger is u dagger x dagger u, and since x dagger is x, that's obvious. Okay, now since x prime is traceless Hermitian, it can also be written as a linear combination of the Pauli matrices, because we know that the Pauli matrices are the complete set of traceless Hermitian 2x2 matrices with coefficients, 3 real numbers, x prime, y prime, and z prime. Okay? So therefore, u, any element of SU2, defines a linear map of x, y, z into x prime, y prime, z prime. Okay. So you can check for yourself that it's linear. For the people who know this, it's obvious. But if you're seeing this for the first time, you should check it. And it's natural to think of this as a three-dimensional vector x vector, and this as another vector x to the x prime. So you see that every element of SU2 maps a three-dimensional vector to another three-dimensional vector. Okay? And the map is linear. Okay? Now the final step of the proof is to calculate the determinant of x. The determinant, now given I erased the Pauli matrices, but I asked the students, I assume the students remember what they are. So x6, remember sigma 1. Let me just write them down quickly. Sigma 2 equal to 0 minus I 0, and sigma 3 is equal to 1 minus 1. So you see that this z times sigma 3, so this is minus z, and this is x plus iy, and this is x minus iy. And we can all evaluate the determinant of a 2x2 matrices easily, and we see that the determinant is minus z squared plus x squared plus y squared. So it's not surprising, perhaps, that the determinant is minus the square of the vector x. Okay. Whoops. Well, this is not showing. Oh, okay. Good, thank you. Okay, so the determinant of x is x squared, but the determinant of x prime is determinant of u dagger x u. So you see that, but the determinant of the product is the product of the determinant. Again, for the students, if you don't remember this fact, you should try to prove it. The determinant of a product of two matrices is the product of the determinant. It's one of the famous theorems in linear algebra. Also, not so easy to prove if you never seen the proof before. So therefore, since determinant of u is equal to 1, then this is equal to determinant of x. So since determinant of x is x vector square, this means x prime square is equal to x square. So it's a map. The u defines a map of x into x prime, and the length of x prime is equal to the length of x. So it maps any vectors into another vector, keep preserving the length. So this is in fact rotation SO3. So for every u, there corresponds a rotation. So this shows that there's a relationship between SU2 and SO3. Now comes the very famous remark, is that SU2, on the other hand, is not equal to SO3, the group, but rather SU2 covers SO3 twice. And what does that mean? That means u and minus u give the same rotation. Now notice u and minus u, if u is an element of SU2, if u belongs to SU2, then minus u also belongs to SU2. And this is not a trivial statement. So you have to, of the unitary part, the u part is easy because it's minus u dagger is obviously equal to u dagger u is equal to 1. And the determinant of u, of minus u, is equal to determinant of u because u is 2 by 2. But this only works because it's 2 by 2, right? Its determinant of u is equal to 1. So if u belongs to SU2, minus u also belongs to SU2. And they give the same rotation. So the group SU2, you should try to picture it. For students seeing this first time, you should imagine the group SU2 covering SO3 twice. It sort of wraps around SO3. And two different elements in SU2 gives the same rotation. Okay? So this is called a double covering. And this is page 246 of my book. And this double covering is one of the, I think most physicists would agree, this is one of the darkest mysteries of physics. Why nature would care about this? Because what that means is that when we rotate through 2 pi, the electron wave function changes by -1. Okay? So you need to rotate by 4 pi in order for the electron wave function to come back. So I would say that this is not totally understood, this deep relation in quantum mechanics. I would say it's not totally understood. And even nowadays in engineering and technology, it comes in, this fact, because quantum computing, as you know, when people talk about qubit, the qubit is just based on the electron spin. So, so the group SU2 and SO3 is has this very peculiar relationship with each other. which is really bizarre. So before quantum mechanics, nobody would imagine that this property of SU2 and SO3 would be realized in nature. Okay, so this shows, by the way, that the two groups are not the same, but the algebra is the same. So the algebra of SU2 and SO3 are isomorphic. So again, this is an exercise for the students. And the way you can work this out is, of course, work out the commutation relation between the rotation, generators of rotation. And for those of you taking quantum mechanics, you know the generators of rotations are called J1, J2, and J3. And you work out their commutation relation, and you show that it's exactly the same as the commutation relation between sigma 1, sigma 2, and sigma 3, between the three Pauli matrices. Okay? So any questions?
Sorry, what about the parity? Because the argument goes on also with switching by a sign and the component of x.
Yes.
So why did you say you get SO3 and not the full O3?
Oh, okay.
In the, I mean,
Yeah.
principle you have a rotation.
Yeah, yeah. Good. Yeah. So let me not go into that right now. Okay, I want to do something else. That good. So I'm going to talk about something. Okay. Okay. So the Pauli matrices have, well, in fact, I just had them here, so let me keep them on the blackboard. 0I, 0. So, so let me keep the Pauli matrices on the board. And so, you know already for finite groups, so I'm assuming here that the students already know something about finite groups. And as I said, I assume the students know about representation. The representations could be real or complex, or complex. Okay? So, you notice that I left a space here between real and complex on purpose. Now, so representation means that given a group element in a group, there's a matrix D of G such that D of G1, G2, I'm sorry, D times G of G1 times D of G2 is equal to D of G1, G2. So these matrices represent the group element. By the way, here, maybe it's worthwhile to make a remark. When physicists talk about group theory, they're really talking about representation theory to a mathematician. So a mathematician considered the group as very abstract, some set of abstract elements, and then there are representation, which are actual matrices. But physicists actually tend to mix up the two. So when physicists think of rotations, they already think about a 3x3 matrix, which to a mathematician is just a representation of some abstract algebra. Okay, so that's just a side remark, not terribly important. So if I give you a set of matrices that represent a group, you can always ask this question. Ask if the complex conjugate is equal to d of g. So this is for all g. If true, then that means the matrices are real. Then the representation is called real representation. Okay? So now, but suppose d of g star is not equal to d of g, then you can say the representation is complex. But not so fast, because this is actually wrong. So if you look at the representation matrices and you see see that the entries are complex, you cannot say it's actually complex, because there's another possibility which I left out here. And this possibility is called pseudo-real. Pseudo-real, yeah, pseudo-real. Okay. Now in physics it was introduced by people like Wigner, but in mathematics I'm sure that people like Hermite and so on probably thought about it. But I don't know in the history of the pseudo-real representation. So, but it turns out pseudo-reality has become very important in contemporary physics right now. Various Majorana fields and so on in particle physics and in condensed matter physics are all becoming very important. And a lot of these things have to do with the fact that SU2 has pseudo-real representations. Okay, so even if you look at the matrices and they're complex, it does not necessarily mean the representation is complex. Okay? Because it could be that d of g star, although it's not the same as d of g, is related to d of g by a similarity transformation. So they're equal up to d and d star. D star could be equal to d up to a similarity transformation. So you remember that when we change bases in matrices, we make a similarity transformation. So intuitively, roughly speaking, pseudo-real means that although the matrices are not real, they look complex, but it could just be related by this transformation. So this is called pseudo-real. Okay? So now, let's see, I guess I push this all the way up. Okay. So now we can go to SU2 again as a. In SU2, the representations of the group elements given by e to the I phi sigma, where phi are 3 real parameters, 3, phi 1, phi 2, phi 3 are real. Okay, so what I'm doing is just writing down what I had before, e to the IH, Lee's solution, right? The 2 by 2 unitary matrix can be given by exponential of IH. H is a traceless Hermitian 2 by 2, 2 by 2 traceless Hermitian. And so it could be written as a linear combination of the 3 Pauli matrices. Okay? So that's what this means. So now we ask the question, okay? Ask if d of g star is related to d of g. So if I complex conjugate, well, when I complex conjugate, I get this. The I goes into minus I, phi is real, and then sigma star. Okay? Now, you notice something, since I had the Pauli matrix explicitly up here, you can see, just using your eyeballs, that sigma 1 and sigma 3 are real, and sigma 2 is complex. It's pure imaginary. So there are only 3 matrices, and so 2 of them are real, pure real, and pure imaginary. Okay? So we note that this is a very special property of this group. Sigma 2, sigma 1 star, sigma 1, sigma 2. So I will now do this by brute force very slowly. Sigma 1 star, since sigma 1 is real, is just sigma 1. But sigma 2 and sigma 1 anti-commute. This is one of the properties I asked you to check. I asked the students to check. Minus sigma 1, sigma 2. So this is equal to minus sigma 1. Okay? So sigma 2, sigma 1 star, sigma 2 is minus sigma 1. And similarly, sigma 2, sigma 3 star is minus sigma 3. But now the interesting case is sigma 2 itself. Because sigma 2 is pure imaginary. So sigma 2 star is minus sigma 2. So it's minus sigma 2, sigma 2, sigma 2, unlike this case in which it's plus. This is minus sigma 2 minus sigma 2, but sigma 2 times sigma 2 is 1. So this is again minus sigma 2. So you see the remarkable property of the Pauli matrices is that sigma 2 turns the complex Pauli the 3 complex Pauli matrices, which I write as a vector, sigma 1, sigma 2, sigma 3. I already done this here, so the notation was clear. I didn't mention it. So sigma 2, sigma star, sigma 2 is minus sigma vector. Okay? So therefore, sigma 2 d of g star sigma 2 is sigma 2 e to the minus I phi sigma star sigma 2. And this, if you think of the exponential, expanding the exponential in a Taylor series, in a power series, then every term, term by term, the sigma 2 changes sigma star into minus sigma star. So it changes into minus sigma. So it changes into plus I phi sigma, which is d of g again. So we see that, in fact, d of s, we identify s is equal to sigma 2, and s inverse is also sigma 2. And so we see that the fundamental representation, or some people call this the defining representation, because the representation is really, it defines the group SU2, is pseudo-real. It's not real, but pseudo-real. Roughly speaking, pseudo-real is almost real. Okay, so now notice this definition. When the representation is pseudo-real, the similarity transformation S is only defined because it's S and S inverse. It's only defined up to a arbitrary constant, right? I can multiply S by any constant I want, and it's still the S inverse. So in general, in particular, since we can define by any constant, we can multiply in particular by I. So this, so we can also choose S to be I S2 and S inverse to be minus I S2, sigma 2. So this means that there's a lot of freedom in choosing S, and so different authors sometimes uses different convention. And you can see from the definition sigma 2 there, if I multiply by I, then S becomes 0, 1, minus 1, 0. So the similarity transformation is just exchanging the upper component with the lower component of the spinor, and with a minus sign. Okay. Now, as I said, this seems like a very, simple thing, and whether it has how it has anything to do with physics. Of course, I already said without quantum mechanics, SU2 would be just a mathematical curiosity. So perhaps in some problems related to rotation, and in fact Hamilton was using quaternions to work out rotations, and so quaternions are basically Pauli matrices. But the amazing thing is that this fact that I showed you here has to do with the discovery of Majorana. That there's one could define Majorana spinors, and so this has become important in both particle physics and in condensed matter physics, as I said. So for example, the neutrino could have a Majorana mass and it is related to the fact that it's this SU2 is pseudo-real. Now, so here I can tell you another little story. When Pauli wrote down the Pauli matrices in 1927, actually Jordan told Pauli that Cayley, so you maybe have heard of Cayley, which worked on matrices in the 19th century, that Cayley had written down the matrix representation of quaternions. And so Cayley already had the three Pauli matrices. But Pauli, of course, ignored him. And so this shows the one important thing that students should learn. Erudition means very little in physics. Nobody credits Jordan with these matrices, but Pauli got all the credit. So if you know a lot, it means nothing. Okay, so now I find this this fact really quite amazing, that about all these facts about SU2. And now one of the frustrations about teaching in the United States, and which I also said in the preface of my group theory book, I think when students learn these things like quantum field theory and gravity and group theory, they should be amazed as well as amused. It's very important to be both amazed and amused. But when you teach these American students at the University of California, when you show them something beautiful like SU2, mostly they just yawn because they didn't get enough sleep or something. So, but on the other hand, recently, a few months ago, I was in Princeton, and then when I was talking to Dyson, to Freeman Dyson, we were saying about somehow SU2 came up, or how SU2, and Dyson got so excited, about how SU2 covers SO3 twice, and who can understand such a thing, and so on and so forth. Okay, so now I mentioned that in physics, I think all of you who have taken a course in quantum mechanics knows that SU2 comes into physics in this very amazing way, which is Pauli, as I said. Now, actually, so students are not shocked at all anymore that SU2 comes in with this -1. So in 1913, as you know, Mr. Bohr said that angular momentum has been quantized in terms of Planck's constant by some integer. And the physics community was really shocked. And but in 1925, Uhlenbeck and Gauss-Schmidt proposed that the electron have angular momentum. The electron spin has half h bar. So then physicists are really, really shocked. And students don't realize how shocking this was. So I would just mention the sense of shock. The Ehrenfest in 1932, which you can see is 7 years later already. Ehrenfest said he just cannot believe this. He wrote that it's an eerie report that a mysterious tribe by the name of spinners actually comes into our physical world. So many of the great men of the time, like Ehrenfest, Niels Bohr, Einstein, and so on, they were all completely shocked. And this could only have been introduced by two young people. So again, this is an inspiration to the young people here. And they were both very young guys. Young guys. And they were in their 20s. So I actually met Uhlenbeck in the 1970s. But he was a very old man. So I realized, but at the time I thought he was extremely old. But now I realize he was only probably 70 years old. From this. Okay. Now, then so this point, I also want to mention the sad story of Mr. Kronig, which some of you know from the Kramers-Kronig relation. He actually lived to 91. I've never met him. And in spite of the name, he's actually American rather than German. But he was born in Germany, but then he moved to the US. And he actually was a student at Columbia. And he actually had the idea of spin half for the electron. In fact, it was earlier than Uhlenbeck and Gauss-Schmidt. So it was 6 months earlier. But why nobody remembers that he had the idea? Because he made the big mistake of mentioning his idea to Pauli, who told him that was complete nonsense. So, and now, it was interesting to see what the objections of famous people like Pauli to the electron spin was. Namely, that if you, at that time they know what the size of the electron is, roughly. They had some estimate for the size of the electron. And if the electron has a spin of this amount, the surface of the electron will be moving faster than the speed of light. So any young person who proposed this would be kicked out of the Physics Institute. You know, how could the electron be spinning and so on and so forth. So there are two lessons here for the young people in the audience, okay? If you think you have a good idea, don't mention it to an older person. You should quickly you should quickly publish, especially don't mention it to Pauli, who then took, once he realized it was a good idea, he took over. The other thing is that if any of the other physicists give you objections, but the objections are often based on contemporary understanding of physics, right? Which at the time may seem really ironclad. So at the time, when Kronig was told that the surface of the electron would be spinning faster and moving faster than the speed of light, I mean, he was completely destroyed. But you can see some of these objections, which at the time seems absolute and that you cannot get out of, totally ironclad. Later, it could be complete nonsense. I mean, nowadays, nobody worries that the surface of the electron is moving faster than the speed of light. I mean, we don't talk in that language, right? So this is very, very important for the young people to keep in mind. Now, I have a footnote to this story. Yeah, sorry. Pavel?
Pauli was at that time like 24 years old.
Also,
You are not
Well, talking to older people, I think Kronig was, in 1925, Kronig was only 21. Young, yeah. But he already had a position. What? That's a good point. But the footnote to my story for young people when they have a good idea is they should talk to older people, but to a good person. So Uhlenbeck and Gauss-Schmidt, they actually talked to Ehrenfest, and they proposed the idea to Ehrenfest. Now what Ehrenfest said to them was that it might be nonsense, but you have no reputation to lose. So that's the definition of a good older person. Okay, so in fact, the interesting thing is that after Uhlenbeck and Gauss-Schmidt submitted their papers, they ran into Kronig. And so they told Kronig about their ideas about spin half for the electron. And Kronig said, I have the same idea, but Pauli told me not to publish because the surface is moving faster than the speed of light. So Uhlenbeck and Gauss-Schmidt got extremely upset. They rushed to the journal and they tried to get their paper out of the journal. But it was too late. The journal said it was already sent to the printer and it's being published. So so they could have also missed the whole thing. But once Pauli realized it was a good idea, he took over. And so then the idea became known as Pauli. Okay, so let me see. I have no time. I'm past the time. I have 5 minutes. So I was going to talk about Cramer degeneracy, but maybe I better talk about it next time. Okay?
Okay.
So, because that actually requires writing down a bunch of equations. Okay? So we stop here.